Hello, today we're going to build a simple DC network, this one here. It comprises of 5 resistors. We've got 2 parallel banks, R1, R2, R3, R4 and R5. Okay? And we're going to build this circuit on something called breadboard. And what I've done with this breadboard is I've ripped off a bit off the back so you can see what it looks like from behind. Well, this is what breadboard looks like on the other side. What we have, if I get my finger in here, we have rows of conductors running horizontally here. And on the outside we have vertical rows of conductors. The idea is that we use the outside vertical conductors, the ones that are going this way, to connect our power supply and ground to. And our components will connect across the horizontal conductors. There's no point in trying to connect them on the same track this way because you'll just get short circuits. If we're using chips or anything like that, we connect them across this side and this side. So there's a gap in the middle so the pins of the chips don't short circuit. So if you are a little bit unsure with resistors and the resistor colour code, what you could do is you could use a multimeter. So I've got both probes from a multimeter connected up to a resistor here. This resistor is brown, black, brown. So using the resistor colour code, brown stands for 1, black stands for 0, and the third band, brown, is the amount of zeros you add. So in this case, this would be a 1, 0 and 1, 0. So this is a 100 ohm resistor that I've got here. So the first thing you need to do is you need to set it to resistance. So you've got a little resistance range here, and the little notch on the dial, that's resistance. And what you normally do with any of these readings is you set it to the highest range possible first of all, and you just make sure that both probes, one goes to common, one goes to voltage at the bottom there. That's for measuring resistance and voltage. You switch it on, okay, and this range is so high it's actually showing no resistance at all. But as we begin to range it down further, we begin to see that we start to get a reading. And the further down you go, the more accurate it becomes. Until eventually you go so far, in this case you can't go any further down, but if you were to go a little bit further down, if you had higher range resistor, you'd read a 1 on here, and that would mean it'd be out of range, so you'd notch it 1 back up. And this one's reading 98.2, okay? Now, I said that the resistor was 100 ohms, but resistors have something known as tolerance. It's impossible to make a resistance that is an exact 100 ohms, for example. The resistors we use have a tolerance of plus or minus 5%. So for 100 ohms, the resistor I'm using could be as little as 95 ohms or as much as 105 ohms. In this case, it's 98.2. Something we need to be aware of. This is a close-up of the circuit you're going to make. We note, if I get my finger in here, we note that the resistors go, as we said, across the parallel tracks that I've just shown you. And we note that the resistors join on the same track at the top, these 2 resistors, and they're in parallel. Remember, the definition of parallel is current has more than one path. Then they join in the middle. All 5 join in on the middle track, and then the other 3 join down the bottom track here. We've got our circuit here. I've got my multimeter and it's set to ohms. I want to take one of the probes, yeah, there it is, and that's going to connect, it doesn't matter which way round you do this, okay, that's going to connect to the top bank of resistors, and the other probe's going to connect to the other bank of resistors like that. It's just going to be like that, top and bottom, okay? And then remember what we said about the multimeter, we just range it down Keep going all the way. And this circuit has a resistance of 45.6 ohms. My resistors from the resistor colour code were 100 ohms, 22 ohms, 33 ohms, 470 ohms, and 330 ohms. From the class teaching, you will know that when we have a parallel bank of resistors, we can use a technique known as product over sum to figure out the resistance of each parallel bank. So for this first bank here, we're going to use product over sum to figure out the value, the total value of the resistance of this parallel bank here. All product over sum is both resistors timed together, like so, divided by the sum of both resistors. Like so. (100 times 22 is 2,200). 100 plus 22 is 122. And when you do that sum on your calculator, it will come to 18 ohms. It won't be exactly 18 ohms, but with resistances you always round it up to the nearest number. In effect, that means that both these two resistors here can be replaced by one resistance with a value of 18 ohms. That's the first part of our calculation. So we will take the first two resistors at the top, and they are 33 and 470, and we do product over sum with that. I've already done the calculations, as you may have guessed, just to save a little bit of time, but I'll write them out anyway. And when you do that sum, you end up with 31 ohms. So we take this 31 ohms here, which represents these two resistors, and we use it to product over sum with the third resistor in the bank. Remember our original circuit? If it makes it easier, you can redraw the circuit if it makes it clearer for you to see. Effectively, we have a circuit that looks like this. When you do the sum, so we can redraw our resistor, or our resistor bank, and it can be represented by 28 ohms. The entire resistance of this bank of resistors is 28 ohms. Effectively, we have two parallel banks in series. We have two series resistances. We have 18 ohms and 28 ohms. Resistors in series are very easy to calculate. You simply add the values together. So we get 18 plus 28 is equal to 46 ohms. RT, the total resistance, is equal to 46 ohms. And you'll recall from earlier learning that whenever we get resistances in parallel, the resistance of that parallel bank must always be lower than the value of the lowest resistor. And if it's not, you need to check your work. When we apply a voltage across an electrical circuit, current flows through the circuit and work is done by the circuit, and therefore we have a release of energy. If we divide energy by time, we have power, and power is measured in watts. In electrical circuits, there are three main ways of calculating power. We can either calculate the voltage times the current, or we can use the current squared times the resistance, or we can use the voltage squared divided by the resistance. Our resistors each have a maximum power dissipation of 0.25 of a watt. If you ask those resistors to do more than 0.25 of a watt of work, they will burn out. So, looking at our circuit as a whole, we've allowed a maximum power budget of 1.25 watts. Because we've already calculated the total resistance as being 46 ohms, it makes sense to use the bottom equation here, because we're going to use the bottom equation to figure out the maximum voltage that could be applied across this circuit. So when we rearrange this equation, we take 46 over to the other side and multiply it by 1.25, we end up with 57.5. So 57.5 is equal to the voltage squared. And when you square root this side, you end up with 7.58 volts. So theoretically, the absolute maximum voltage we should apply to this circuit is 7.58 volts. You need to choose the next lowest voltage from your table, and the one that I'm going to use for this circuit will be 5 volts. The next thing you'll be asked to do is to work out the total current flowing through the circuit. So we would have, obviously, I'll sketch them out very quickly, our resistors. And we've got a voltage supply of 5 volts. And we'll get a current flowing through our circuit. Now, Ohm's law tells us that the current flowing through a circuit, I, is equal to the applied voltage across both ends of the circuit divided by the resistance, the total resistance of that circuit. And when you do that sum on your calculator, you will get a result. Mine's 0.108 amps. Your result will obviously be different because you'll have a different total resistance and probably a different voltage supply. But that's how you work out the total current, IT, flowing through the circuit. So here we've got a very nice close-up of the circuit with the, what you can see there at the moment is the voltage applied to the circuit. We can quickly show you the power supply as well. Now, this is very interesting because the power supply is set up at very close to 5 volts. But on the right here, as I'm looking at it, you'll see the current is 118 milliamps. Now, that's quite significantly out from our calculation, even where we rounded up the resistance. Whilst we're at it, power supply, main switch on, current must be switched on here, on this one, here. Positive and negative. We've got coarse voltage control and fine voltage control, and I'm just going to adjust the fine voltage control here, get it in shot, and we get that close to 5 volts, like so. Zooming out, this is the whole circuit here. The meter on the right is reading current, and the meter on the left is reading voltage. Now you'll notice that the power supply itself says it's got a voltage of 5 volts, but our meter reading gives us 5.46 volts. That means that the voltmeter in the power supply is uncalibrated, and it actually needs to go away to be calibrated. It's giving a false reading, and quite a significant difference. Two things to mention also at this point. When we measure current, it must be in series. So I'm going to trace through the current, the way that we measure current. So if we look through, we go from the power supply here, there's my finger, found it in the end, and that comes out and it goes to the amps in, this one here, and we make sure that on the meter itself we're on amps DC, there. Just zoom right in on that, there we are, amps DC. Then we come out the common of the meter and into our circuit there. And then the other side comes out to the other side of the circuit, and that goes back to the power supply there. This is very difficult to do. So current's measured in series, but voltage, which is this one here, is measured. So we've got both of our voltage leads. We set up for volts DC over here. Voltage positive, the common connection, and they are measured in parallel. So these two connections here, this one here and this one here, are measuring the voltage applied across the circuit. The calculations we're going to do now are the ones that give people the most trouble in this circuit. So I'm going to draw out the circuit, and we're going to measure, firstly though, we're going to calculate the voltage across R5, and we're also going to measure the current running through R3. And you recall two things. Firstly, that voltage is always measured in parallel. So the voltage must be measured in parallel across this bank of resistors here. And current must be measured in series. So if I've got the current flowing into this parallel bank here, it must flow through an ammeter, through the resistor, and on through the rest of the circuit. We will start with the voltage. You will recall that this entire parallel bank of resistors, the two resistors, is equal to 18 ohms. So we can use that 18 ohms to calculate the voltage dropped across this bank of resistors here. Recall, Ohm's law tells us that voltage, the voltage dropped across a component, a resistive component, is equal to the current flowing times the resistance. Now what we have to be aware of is the current flowing through this bank is the current that is flowing through the entire circuit. It's the current that we've already calculated to be 0.108 amps. The resistance of this parallel bank is equal to 18 ohms. Therefore, the voltage dropped across this bank is simply 0.108 times 18. The voltage dropped across this bank is 1.95 volts. Now, a very quick check of this, what we could do is we could very quickly work out the volt drop across the other bank, and if both volt drops added together equal 5 volts, we know we've done it correctly. So we know that the resistance of the other bank is 28. So in our calculator we can just plonk in 28, times it by the circuit current, 0.108, 3.024. So when we add this voltage together and this voltage together, we get approximately very close to 5 volts. That's known as Kirchhoff's law for further reference. Now the current flowing through this resistor, we have to go back to Ohm's law again. Ohm's law tells us that the current flowing through a component is equal to the voltage applied divided by the resistance. As luck would have it, we just calculated the voltage applied across this bank of resistors here. And we calculated it to be 3.024 volts. You'll recall from an earlier video that the voltage applied across a parallel bank is applied equally to each resistor. So the 3.024 volts is applied across this resistor, it's applied across this resistor, and of course it's applied across this resistor. So the current can be calculated by using the 3.024 volts and simply dividing the value of this resistance into it. This resistor, you'll recall, has a value of 330 ohms. So on the calculator that comes out at 9.16 times 10 to the minus 3. Now to write that as a number that most people would understand, it's very simple. All we do, the minus 3 means we go 0. So 0, that's 1, 0.0203,916. And in milliamps, that would be 9 milliamps, 9.16 milliamps. And what we're going to do now is we're going to check that using our instruments. So here's our basic setup. Looking at the power supply, I've adjusted that so that even though it reads 4.52 volts, when you check it with the meter, it's 5 volts now. Firstly, we look at our voltage dropped across a parallel bank, and that's 1.98 volts, very close to what we calculated. And the connection itself on the circuit is, here is R4 and R5, and we simply go across them like this. So that's the voltmeter connected up there. Bring it right in close so you can see that. It shakes. This is the current connected up here. Once again, notice the difference. And the current is reading on the scale, so we're a 20 milliamp scale here, the current's reading 9.37 milliamps. So that's once again very close to our calculation. Looking on the circuit itself, we've got the current comes in, so there's the power going into the circuit. It comes through here, goes into the meter there, it comes out of the meter, and what I've done is if you can see it, what I've done is I've just disconnected the resistor and connected the ammeter to that, so the current's got to flow through that resistor and it's got to be in series. That's about it. That's all you need to do to complete this outcome.